Hello students, welcome back. Let's go back to section 2, discrete probability distribution. We went through the meaning of discrete probability distribution to a certain degree. And what do you mean by probability distribution? Either PMF or CDF or both of them together. We talked about what is PMF and then we talked about what is CDF, and also we went through a problem that determines CDF when PMF is given. We can of course generalize to arbitrary situation. Now, how about the other way around? If we know CDF, how can we find PMF? Let's go backward. Here's an example problem. Now, CDF is given there. So first interval from negative infinity to 0.25, the probability or cumulative probability is 0. Yes, this is CDF, so everything begins from 0 and ends at 1 with increase by jump. Now next class interval, 0.25 to 0.5, 1/3. 0.5 to 1.25, 1/2. Yes, we got an increase. 1.25 to 2.00, 3/4, and finally, in the last class interval, 2.0 or higher, total 1. Yes, this is a valid cumulative distribution function. Going from 0 to 1, just increase, nothing more. And we have jump in several places, and also, finally, the structure of the class interval. Semi-inequality to the left, strictly inequality to the right. Yes, everything fits. This is a valid CDF. Now let's find out the PMF. Okay, all right. So let's erase all those and prepare the table. Okay, all right. Now look at this, and you can see where the break or jump is taking place. What is the smallest x value that jump is taking place? 0.25 and 0.5 and then 1.25 and 2.0. Is that clear to everybody? Is that clear to everybody? Otherwise impossible, so otherwise probability is 0. So 0.25 is the threshold here that separates these two intervals, and 0.5 and 1.25 and finally 2.0. Something is taking place. Something took place so that 0 became 1/3. So what's the size of the jump? I can figure it out by subtracting. Now 1/3 to 1/2, a jump took place. How much? I can subtract to find out. 1/2 to 3/4, a jump took place. How much? I can subtract to find out. And finally, 3/4 to 1, size of the jump, I can subtract to find out the size of the jump. Okay, let's do it. 1/3 minus 0 is 1/3. Great. 1/2 minus 1/3, what is it? It's going to be 1/6, right? This is equal to 3/6, and then this is 2/6 if you take this common denominator, so it's 1/6. Now 3/4 minus 1/2 is the same as 2/4. So if you subtract, you're going to get 1/4. And finally, 1 minus 3/4, 1/4 is the jump size. Now tell me, is this valid probability mass function? Do they add up to 1? Check. Is this right? Well, let's go ahead and do that. Alright, we did some color coding as well. So jump takes place at 0.25, 0.5, 1.25, and 2.0 respectively. Color coding would help. You see, blue, red, green, and brown. Okay, those are the jumps. And then mass function, you can find those out by subtracting. And then if you do that, you get all these. Yes, of course, same as what I got before. And then is there a graph? Okay, alright. This was the previous graph. And then superpose that with the probability of the mass function. And what do I get? Jump size the same as dot height. And this height and the height of this dot is the jump size. This height is the same as the jump size. This height is the same as the jump size. Yes, everything fits. So that's how you can determine PMF from a CDF. The keyword is cumulative, so keep adding up. That's how you get the CDF, right? So you have to go backwards. So you have to take subtraction this time. Subtraction, subtraction, subtraction. You can do the same thing even when your function, your expression of CDF is given in a piecewise defined function format. It's the same deal. The detail is left to the students. So what did you do so far? We discussed what is PMF, went through some examples, went through CDF, went through some examples. That was a bit harder. And then conversion. When PMF is known, how to find CDF. We did that. And vice versa. If you know CDF, how to find PMF. From PMF to PDF, keep adding up the probabilities because this is literally cumulative. So you have to keep adding up. And then going backward, you have to keep subtracting. And then because of this relation, PMF is known, then CDF is determined, and vice versa. Known CDF, then PMF follows. If any one of them is known, then the other is also known. So we can call the discrete probability distribution as either PMF or CDF or both of them put together. So that is the answer to this question. What is so-called a discrete probability distribution? Now let's go through some proof problems, maybe. Some properties of probability mass function. Okay, any probability values between 0 and 1, so yeah, okay, here we go. And then at specified xi values, we have probability mass, which add up to 1, otherwise 0. And yes, those must add up to 1. And then the graph consists of dots, or those with vertical line segments, or you can use rectangles and use probability histograms if you use rectangles of same width and none of them overlap. But of course, I don't like those probability histograms very much at this moment. Sometimes they're more useful, but at this moment, no. I prefer those dots. Okay, how about the properties of cumulative distribution function? As we saw before, it's a step function, increases from 0 to 1, and then each step has a jump, and that jump size is the probability mass, the PI. And then f of x is probability mass thus far. Oh boy, okay, this one is a little bit hard to understand. Let's go to an example problem like this. Let's see. Is this an example of CDF? Okay, all right, here. Okay, f of x value is identical 1/3, where x is between 0.25 to 0.5. So it stays the same. That's what this thing is talking about. In the class interval, semi-inequality to the left and strict inequality to the right. That's the structure. Always remember that, please. If you scored precisely 80, then you belong to 80 to 90 group, not 70 to 80 group. Semi-inequality to the left, strictly inequality to the right. That's the class interval. In that case, f of x value stays same for all those x values in the same class interval. And that is the sum of the probability masses thus far. Oh boy. Left-hand side limit versus the right-hand side limit. Function value is the same as the right-hand side limit, not the left-hand side limit. Let me skip this. Getting a little bit too complicated. I mean, the proof is here. No, not the proof. I even skipped the proof in this notebook either. Getting too complicated. Even though everybody went through calculus, this is a bit too much, so let me just keep it at that. Just remember it as a result. And then if you want a probability from any interval b to a, then you do that by subtracting, appropriate subtracting. So probability is the difference of function values, capital F of b minus capital F of a. This resembles the fundamental theorem of calculus. If you think of that way, then you're not wrong. It is related to that. And as for this a minus, that actually is causing trouble. That's because there are discontinuities and all those kind of things. Okay, let me stop at that. I'm not going to go overboard on these kind of theoretical stuff, at least not just yet. Okay, am I done? I guess so. I am finally done with section 2 of this notebook, and I'm going to talk about section 3 and section 4 in a separate videos, or more than one separate videos more likely.